All right, let's start lesson 2, where we're going to go deeper into the time series analysis. As we said, time series analysis is a sequence of data measured at successive points in time, daily, monthly, quarterly, annually. And good examples are GDP growth, stock prices, inflation rates, unemployment rates. And these observations are time oriented and often exhibit temporal dependence. So the value in one point is related to values at previous points. That's when it's autoregressive. It's an autoregressive process. And time series focuses on one entity observed over many time periods, because if we're looking at more than one entity, we move to panel data. Okay, so the three main concepts here that are important for us to start talking about time series analysis is stationarity, autocorrelation, and white noise. So going straight to the point, stationarity, it's a crucial concept, because if we work with time series that are not stationary, we're probably going to have spurious regressions. So in essence, it's a false relationship. We can try to find relations between variables that are false. So we have to work with stationary series. We're going to get deeper into that right after this. Autocorrelation is when we're looking at time series analysis. We're thinking about what happens to a dependent variable because to that variable according to its own values in previous periods. So autocorrelation means that when we're talking about a model like this, typical dependent variable, then we have some starting point here, and then something like this. This t minus 1 means the same variable, one in a previous period. So if this exists, it's an autocorrelation. So because we say that the variable that we're looking at, the dependent variable, depends on itself on a previous period, or one or two or three or as many previous periods that are important to predict the value. And this is AR, it's autoregressive, and MA is moving average. We're going to talk about these models right after. And the other important concept is the white noise, because usually when we have an equation like that I showed, something like this is a beta, right? It's not a b, it's a coefficient. So usually when we have an equation like this, I'm going to put t minus 1, which means one lag, one observation before the time that we're looking at right now. Most of the times we'll have this little e with the t here. This little e represents that's part of the value that we're trying to predict is not related to the variables that we put in the model, but it has some random oscillation that we can't predict. It's called white noise because it's got this specific characteristics of zero mean, constant variance, and zero autocorrelation at all legs. So if a process has these three characteristics, it is a white noise. And that's what creates what we call a stochastic model. Because if we run an experiment on physics, for example, if we measure the time for something to fall, or the time for a certain substance to heat, if we do it again, the same experiment in the same conditions, we're going to have the same values over and over again. Like if you get the time for a certain body to fall from a certain height, if we do it again and again and again, we're going to have the same time again and again and again. When we're talking about data that are not deterministic, those things oscillate. And this oscillation, when this oscillation is not perfectly predictable, most of the times it is a white noise, and then we put this little e here to represent this error that we can't predict with the variables that we put in the model. And that's the nature of trying to predict something that is not exact, as it is in physics, for example. So white noise is this little variation here that we can't predict, we can't model, and causes the variable to oscillate in a way that we can't predict previously. Okay, this is the concept of white noise. And let me go a bit further into stationarity. So look at those two variables here. It's clear the difference that this one goes around a certain value here, in this case 0, and it's got something that looks like a ceiling and a floor. It doesn't go much over those bands here. And then this variable here is one that goes up. It has a tendency of going up, right? When we have a variable that oscillates between a certain value and have a mean in which it oscillates around, we call this stationary. When the variable behaves like this, in this case it's going up, but it could be like this as well. It could go down. It doesn't go around a certain value. It doesn't have like a range from which it oscillates. We call it non-stationary. And as we said, what's the problem of working with non-stationary data when we're doing econometric analysis? Is that you're probably going to get fake coefficients. You're going to get coefficients that don't represent something real, spurious correlations. That's what we call. So we should avoid using non-stationary variables as much as we can. If you're working with non-stationary data, it is possible to solve this problem, and we're going to talk about later. Just for you to see a real example, real life example, this is the exchange rate between the US dollar and Brazil's currency. And one US dollar buys around, you see here, 5 units of Brazil's currency. And it, as you can see, is not around a certain average. It was at a certain level here, and then it went up, and then went down a bit, but it's completely different from a series that would go around a certain average, right? So this is non-stationary. And if I'm trying to predict the exchange rate between the US dollar and Brazil's currency using this data, I can't use the pure data like this. I have to change the data. And how do I do this? We do what we call the differentiation. This is the first difference. Well, what's this, right? See, this looks stationary because it is within a certain range and it goes around a certain average here, in this case also 0. Why is that? What's this data about? This is the variation between days. So if I get the difference between, let's suppose that those points are days, right? So what's the difference between this day and this day? And then from this, for this, and so on for all the difference that I have here. And I put that into a percentage. So like suppose in this day, there was like a negative variation of 0.5%. Then the next day, it was a positive variation of 0.3, and it's so on. In the end, I'm going to have something like this. Like I'm measuring the variation between one day to the next. So it's not the pure exchange rate, but the variation of the exchange rates from one day to the other. And then this series has the type of behavior that I can use in econometric analysis. It's got a variation that behaves within a certain range, and it goes around a certain average here. This seems to be a stationary series, the first difference. So I can use this series of the first difference into the models that I'm trying to build, but not the pure model, not this exact value here. That won't give me a real coefficients. And how do I know that the series that I'm using is stationary or not? Because sometimes I'll have series like this. Then it goes up. It has like a behavior of stationarity, and then it goes down, or it oscillates. All those things are possible. Those things exist in real life. Series are not perfect, are far from it. Then how do I know that this series can be used in an econometric model or not? For this, we have those two tests, the ADF and the KPSS, Dickey Fuller and those guys here. They're the authors that proposed the model. And then we run those tests to see if the series is stationary or not. And there's a decision rule here, a low p-value below 0.05 rejects each decision the series is stationary, and the same thing for the other model. And when we run these analysis on our softwares, it usually shows the result straight away. So we run the analysis, it shows the coefficient, and then we can know by considering the coefficient if we reject the hypothesis and consider it to be stationary or not. Specifically for those two tests, there is a practical interpretation, which is if the ADF p-value is low and the KPSS p-value is high, you can proceed with the modeling. If it's the contrary, pretty much the opposite, you have to do the differentiation. Is that thing that I showed you, that instead of using the series, we use the difference between values of the series. And if it's ambiguous, if both are high or both are low, then you probably will have to think of something else. The data that you have won't be useful, and unfortunately, in real life, this happens. Like you collect a lot of data, and then you run the analysis, and it's ambiguous, or the tests come up with coefficients that are not useful to predict anything. Unfortunately, that happens. And sometimes, actually, in reality, when the data comes in a very good shape, then you build a model and it comes well, comes good. The values work really well. The model works really well. Pay attention, because many articles in history have been how can I say, manipulated to fit for the tests to look like the discovery was very good, and they use fake data. That has happened in history many times. So real life, when you use real data collected, usually the tests won't be perfect. They will have some room for questioning, and that's a good thing. Like if you present those results, it means that you really that you really collected real data, that you're not faking it. But yeah, that's how we have to consider the tests. And I will show you how this works in using the softwares when we go to a lesson 4, I guess. We were talking about white noise, right? Which is this little e that you see at most equations when you're talking about predicting models. And white noise is a random process with zero mean, constant variance, and zero autocorrelation at all legs. This is an example I got. I found this example on Google, which shows a white noise, like random variation, zero mean, constant variance, and zero correlation with all legs. Those are the values of some white noise oscillation, where I told you at the other slide, that is this little e thing, variation that we can't predict the variables that we put in our model. This it's a good thing to exist there, right? Because if it wasn't for that, we would be working with natural phenomena. And then, what are the models? Going straight to the models that we use when we want to predict a certain value. So the first type is the AR models. AR stands for autoregressive models. And the idea is I have my dependent variable here. Here is like a constant. And then I have one coefficient that applies to the variable in a previous period. And then I have another coefficient that applies to the value of the variable on 2 previous periods, or the value of the variable on 2 legs, 2 times before what we have now, and so on, to as many as my model considers good. until we use this p value to show that it can goes up to as many as we consider proper. And the variation here, the white noise here. Yeah, I put here the order of the AR process, coefficients, and the white noise error. So the second type of model that we use is the moving average model, which has the idea of using here the dependent variable, considering that it depends linearly on current and past white noises error terms. It's kind of hard to explain why this happens. I don't think we should focus too much on why the past white noise error matter. Because if it's a white noise, it shouldn't carry any specific information on it, right? Yeah, that would be the idea. But in real life, sometimes it makes sense to use that white noise error to predict the next variable. That's probably an indication that the variables, the series itself is not enough to represent. It needs another variable that's not in the model, in the full model. But still, luckily today, softwares do this analysis for us. So if using an MA model to improve the prediction capability of my model here, if this makes sense, we run this analysis on the software, and it brings us the answer. So just for you to see how the equation works. So it's pretty much the same idea, dependent variable, and then I have the white noise here, and then I have a coefficient that applies to this white noise error on a previous term, right? Here on a previous period. And then the same thing for 2 previous periods, and so on until as many as I want. Not as many as I want, but as many as the tests define as the best legs that we must use. So just for today, for the purpose of your analysis, just understand that it's an autoregressive process, and when you have moving average, the error also matters to predict the value. And then if you combine them, and you can, there's no problem about it, you combine AR and MA, and you have the ARMA models. And as we were talking before, if I have a series that behaves like this, and then I want the series to behave like this, I can do the differentiation that I told you about. Then I can simply see the difference between this value and this value, one from one data period to the other one. And then I have the variation, just the variation becomes another series. And if this series is stationary, I work with this one, right? So if this process is called integration. So when I don't use the variable itself, but I use the difference of the values of the variable over time, that's the differentiation. And if I do this once, this d here, this little d here, which is this order of differencing, the number of times that the series has to be differenced to become stationary. So if I do this once, it's the number here would be 1, right? If I do this twice, sometimes if I'm, just for you to know why this happens, because sometimes if I have a series that behaves like this, and I do the first difference, it's going to look like this. And then the second difference is going to look like this. So if you have something that's looks like a log graph, then the first difference will probably look like this, and it's still not stationary. And then the second difference will be enough for you to use as a series here. If you have to do the second difference, it's going to be harder and harder for you to come up with a result or analysis, but just for you to know what this representation means, right? So ARIMA models is the AR integration here, the number of times that you differentiate the series to make it stationary, and the moving average models. Okay, and now the important question, right? How many legs do I use when I'm trying to build a model? And there are 2 methods that we use that most papers use, so that's appropriate for you to use if you're analyzing data or writing your article, which is the partial autocorrelation function which is it's kind of a graph. It's a plot of data that you can use, and the information criteria. The information criteria are more viable. It makes more sense for you to say that, for example, I choose 2 legs. Why? Because of information criteria consider this to be the appropriate number of legs. It makes more sense than the partial autocorrelation function, although they will most of the times walk together. The result that you'll have here will be the same result that you have here. It's just that this one, it gives you like a graph, a visual representation of how it works, and this one is just a number that must be analyzed mathematically, but don't worry because softwares do this for us today. And to finish this time series data analysis, I would like to say, to wrap up, that time series is good for forecasting one specific type of data, which is usually high frequency data of a single entity. Most of the times, our idea is to try to predict the future. That's what people looking in stock markets, they look at all the time. They're trying to predict the price of a stock in the next day or the next week or the next month or year. And what economists do all the time to try to predict series variables that depend on decisions. So we can think of unemployment rate, for example, because unemployment rate today, it's highly correlated to the unemployment rate in a previous period, right? It doesn't go up and down randomly. The unemployment rate goes little by little. It changes every time you get a different data. You have something which is last times value plus or minus something. And that's the idea of time series analysis for us to predict future values. And ARIMA models are the ones that we use the most. We're going to talk a bit about VAR. GAR is mostly used for financial analysis to estimate volatility. And VAR is a methodology that uses autoregression, but also uses other variables. So that's what we call vector. It's a vector autoregressive model. And we also use machine learning approaches to try to solve this, try to predict variables according to time series. So this is what we have for now. Our next class will be about panel data. And after that, I'm going to show you how to use that in a software so you can get your data and run this analysis, find the best model, come up with the coefficients and the results, and then analyze these results to write the conclusion that you want, right? So this was the theoretical introduction to time series. And in the next classes, we're going to go straight to the software and use the data to get the coefficients. All right. See you in our next lesson.